I hope that everybody understands that we decided to give lecture today. Again, I apologize, but I was really again in trip, and I was not sure that I will be in time today. But everything was okay. So we what we did in the previous lecture, we obtained the expression of metric tensor. By the way, I would like to ask, do we have some additional lectures, not only on Monday and Friday, but something additional? Did you check? Are you here?
Yeah, we're here, but don't check.
As I understand, we need to finish. I will try to check now. No, I will not do it quickly. Okay, I will check, because it looks that due to the fact that we will need to finish our lectures early in December, so we will have some additional lectures, third lectures during each week. Unfortunately, I don't have any information. I need to check. I need to go in my how call it room of the professor, which is so I have to check it. So I will do it today. Okay, so let's start. And what we want to obtain, and now we can do it. We want to obtain Einstein equation. So Einstein equation, it means that we want to obtain the equation for gravitational field. To do this, we found the zero component of metric tensor, which can be expressed through the phi, through the gravitational potential of classical mechanics. And somebody forget to switch off his microphone, and maybe this is Sergei Kirillov. Sergei, please switch off your microphone. Popkov Sergei. If I do like this. Okay. So, okay. What we want to, the idea is such a way that we will start and we will obtain the equation of gravitational field from Newtonian case. So to generalize Newtonian case for general case for general relativity. Let's remind. I will remind that in the case of the weak gravitational field, we have again classical mechanics. The gravity we can describe Poisson equation. Poisson phi equal 4 pi g rho. So it depends. We can put minus. It depends how we determine the potential, the gravitational potential with a minus or with a plus. So what is important that we have, and if you remember, this corresponds to the case of the inner gravitational field. So it means that if we have, if we have some body, for example, okay, I can put here like this. So in this case, can you hear me well?
Yes.
Okay. So it means that if we would like, I will just to remind very famous Dirichlet theorem for the gravitational field of the body. And the Dirichlet theorem tells us that if we would like to find the gravitational potential of the in any point for the case when we have some body. Okay, as an example, I put the spherical symmetric body. It means that for the inner part, we can describe it, we can find the gravitational potential, solving the equation, the Poisson equation, this one, and this will correspond to the inner part of the body. For the outer point, if we would like to find the gravitational potential outside of this body, so we need to solve Laplace equation. Laplacian phi equals 0. So Laplacian, this is second derivative from the potential by coordinates. Okay, so this is for outer potential. I'm sorry, but I prefer that Sergei Kirillov, are you here? Not here. Oh, okay. There's some, background noise issues. So, if we will solve, we know this from a classical mechanics, especially my students who was presented in my lectures of celestial mechanics. So we did this procedure for some cases. If you will solve together all these two equations, finally you can obtain the expression for gravitational potential. Of course, as you remember, we need to take into account that the potential, and due to the fact that gravitational field can be continuous function when we go from outer part to the inner part like this, so it shouldn't be any jump of the gravitational field. And in this case, we also need to take into account the saving of the solution for the outer and for the inner potential. So in Dirichlet, and this is called Dirichlet problem, when you find the function, so the Dirichlet problem, I just will remind that if you have some function which satisfy Poisson equation in inner part of the body, Laplace equation in the outer part of the body, and this function is a continuous, has the first derivative and the second, and this function in such a way that on the boundary, I will put like this, outer equal phi b boundary inner, and the same for the first derivative, I will put like this. Outer derivative b phi in derivative b. So this function we call, this function correspond to the, or coincide with the gravitational potential of the body, and this is in classical mechanics. So now it's just, to remind you why we speak about Poisson equation. Now we want to find the gravitational equation for relativistic case, not only for the weak, when we speak about classical mechanics, we simultaneously understand that we speak about weak gravitational field. So now we want to find the equation for the strong gravitational field. It means that which will correspond to relativistic case. In this case, we will use as a limiting case here again. Poisson equation. I will remind that in Poisson equation, G, this is gravitational constant, rho, this is density. So this is normal density, and the dimension of the density, this is mass divide on L cube, where L, again, this is some scale in the space. What I would like to say that, and we will see that final equation which we will obtain, it's a non-linear equation. So, and it should be non-linear equation. Why? Because we understand that the body which create gravitational field curve the space. From one side of our idea that the gravity coincides with the curvature of the space. From another side, the curvature of the space tell matter how to move, how to distribute. So this tells us already that the equation should be not linear in this case. It means that it's the non-linear properties of equation of gravity represent the fact that the action of the gravity made the action on himself, on itself. So now we will try to generalize Poisson equation for the relativistic case. And we immediately understand that if we speak about the relativistic case, we need to involve speed of light, because all time when we speak about relativity, special relativity, and of course it will correspond to general relativity, it should appear speed of light. Due to it's all time when you can see the speed of light, it tells you that okay, it means if we compare classical mechanics with relativistic mechanics, it immediately tells you that you are working in relativistic mechanics. So if we will take into account the special relativity, we understand that we need to go from density of the body, we need to go to energy density, so to epsilon. Epsilon, it means that we need to multiply rho, which is just the volume density, on c squared, where c it's the speed of light. So, and it is understandable, yeah, okay, it's by, if we will put the dimension of energy density, so this is energy density. We will have mc squared divided on L cube. I even keep here the letter C instead of V. Usually when we write dimension things, I put V. So just to show you that this is exactly dimension of energy. Okay, it means energy divided on L cube. So also I will now to take into account this expression of metric tensor, which correspond to the case of the weak gravitational field. So it means what we did before, this one, 2 phi divided on c squared, okay? So, and I will consider the Laplace operator. So a Laplace operator, I will put Laplacian G00. And from this expression on the left, I can immediately see that this will be 2 divided on c square Laplacian phi. By the way, you can understand and remember why we need to put here 2, because this is due to the fact that we consider the series of the when we consider here, put here. Yeah, so in principle, it tells us when we consider the series of the square root. Okay. We have here square root, so this one. This related with the appearing of this 2 in our expression. So in this case, let's do some simple procedure. So we will put 2 divided on c square on the left part. So it means that I can write like this: c square divided on 2 Laplacian g 0, 0. This is equal Laplacian phi. This is equal Laplacian phi. Okay, like this. But from another side, we know, due to this equation, that Laplacian phi equal 4p g rho. Okay, so I can write here that it will be 4p g, and instead of rho, I will put from this expression notation energy density. Okay, I obtain that rho equal epsilon divided on c square. So in this case, I will put here divide on c square, multiply on epsilon. Or finally, I can write that Laplacian g 0, 0 equal 8p g divided on c 4 epsilon. So what we obtain? We obtain we obtain the equation for the case, in principle, this is relativistic equation, which correspond to the case of the weak gravitational field. Of the weak, but in any case, taken into account the relativistic properties of the gravitational field. So now we want to generalize all of this for the case for the general case. So for the general case, we can we can write generalize this case for the case of the strong gravitational field. So for the strong gravitational field, we can write intuitively, we can write like this. So this is only, you can see the components and the metric tensor 0, 0. I can suggest, and possibly Einstein also, think like this. I can generalize. I will put for the general case, it means that I need to write everything in tensor form, because we understand that if we have an equation in tensor form, it means that it will work in any reference system, in any coordinate system. So, and I understand that I need to put some tensor in the left part, and it should be tensor of the second rank, some tensor, for which the 0 component should be Laplacian J00. We will write the properties a little bit later. On the right side, we can keep this dimension part. And since we have tensor on the left part, we need to put some tensor in the right part. We just need to remember that if we consider the zero component, in this case, we already can speak about four-dimensional space-time. It means that k equals 0 correspond time coordinate, and k equal, I will use such a kind of notation that when I use the Greek letters, it will correspond to space coordinates. Okay, so I just need to correspond to this case, which we obtain here, that this equation, which we wrote general case, should satisfy to this equation for the case of the time coordinates. Okay. Now we need to understand, but what exactly should be this tensor Jik? What is this? This is of course question. About this one, we can in principle understand that it should be tensor of the energy momentum tensor. So in principle, in advance, we can write that Tik, this is because for the matter we have only this tensor. It should be energy momentum tensor. Because indeed, if we consider some energy momentum tensor for macroscopic bodies, for hydrodynamics, for example, we know that the energy momentum tensor Tik we can represent in the following form. So this is P plus epsilon, where P, this is pressure. You should remember this from your lectures before, in, for example, lectures electrodynamics or hydrodynamics, minus P Jik. So where this I, this is four-dimensional velocity. This is four-dimensional velocity. So later we will consider it much with much more attention. So for this four-dimensional velocity, I just remind that this is 1 divide zero component. This is 1 divide 1 minus v squared divided on c squared, and three-dimensional velocity divide on like c, and this is 1 divide v squared on c squared. So this is four-dimensional velocity. And this is what we have for example, for energy momentum tensor. Exactly when we will consider the case when we will work with the model of universe, exactly this expression for energy momentum tensor will be important for us, because and we will speak about this, how we can describe the distribution of matter in the universe if take into account the universe and structure of the universe enough complicated, but we will do some simplification. And in principle, we will consider this like a continuous or some special medium which can describe the distribution of matter of the universe. And we will do it a little bit later. This is what I would like to say about energy momentum tensor, which is on the right side of the equation of gravity, which we would like to find. And again, we understand that tensor energy momentum tensor describe the matter from one side. From another side, we need to understand this part. On the left part, again, we remember that our main idea is in such a way that we describe gravity as a curvature of space-time. You can all time remind this experiment, Gedanken, it means thought experiment, not real, but which you can imagine, with a rotating solid disk. We spoke about this before. So, and it's understandable that this tensor GIK should describe some properties of the space due to gravity. And we need to understand what is this. To understand it, in the first, we need to, we understand that this tensor, let's go in the second page. So I will put here just for convenient. And you know, for example, you immediately can see that why we have and understand why we have here 8 and P. So this is memory of the Poisson equation. All the time we need to satisfy the classical mechanics, so the limiting case of the weak gravitational field. C, we also remember why we have a C, because this is speed of light, this is relativistic theory. G we also need to have because we are working with gravity and we need to have a gravitational constant. So everything, you know, understandable why we have such a kind of multiplier here. So now let's think what is it, what this tensor on the left part. We in principle understand that since in the weak, sorry, I write, not right. Weak, okay, I will write weak case, which is understandable that this corresponds to the weak gravitational field. GIK correspond Laplacian, yes. It's better to write Laplacian G 0. So can we recognize which dimension of this tensor should be? Must be. Please tell me. Which dimension of metric tensor? Are you here?
So,
Yeah, I want to understand which dimension should be this tensor.
oh,
Dimension.
I think that it should be 1 divided on L square. Why? Because metric tensor doesn't have any dimension. It's a dimensionless value. Why? Because when we write even our, interval, so dimension of this interval correspond to dimension of this dxi, dxk. It means that metric tensor doesn't have a dimension. Okay? In principle, we can check a dimension of the right side of this equation and also to make a decision, to make a conclusion which dimension should be. Okay, let's consider the dimension, because sometimes dimension is very important to be sure that we are doing everything right way. Okay. So doesn't matter about 8p. So it means that we need to put dimension G, dimension V4. The zero I know that from this consideration, I know that zero component of the energy impulse tensor, energy momentum tensor, should be energy density. So, and I can put here epsilon. Okay, let's look what final dimension will be. So if I don't, for me, it's convenient to consider, to find as usual the dimensional gravitational constant like this. So I just write the quality of the kinetic energy on the potential energy. So from this, I can find the dimension of G. Okay, it will be V square multiply on scale L divide on M. So here I will put V square L divide on M multiply on V4 and energy density. Energy density, this is energy divide on L cube. Okay, but instead of energy, I can put the dimension, because energy, this is mv square. It's a dimension of energy. So, okay, in this case, I can see that m disappear. V, this also disappear. So this and this we have 2. And finally, really, we have a dimension on the right side, 1 divided on L square. So we can see really that the right side of the equation, this equation, have a dimension L divided 1 divided on L square. From another side, against we understand that it should correspond to the fact which I wrote here, that and here. So because I will put here dimension of Laplacian. Okay, this is 1 divided on L square. And since metric tensor is dimensionless, so we obtain that this tensor GIK, it's a dimension of 1 divided on L square. So this is what we understand for now. Okay, it should be some tensor which has a dimension 1 divided on L square. We also need, we have also taken into account that this tensor should satisfy, must satisfy some properties. The first property of this tensor, that GIK should be really tensor. It must be tensor. Since on the right side we also we have a tensor, so from the left side we also need to have a tensor. And again, we need to have an equation of gravitational field which is correct in any reference system. The second property, we also understand that this tensor should consist of some object which describe the property of the space or property of coordinate system. And we understand that this should be metric tensor. We even can see here that the zero component of metric tensor is here. So it means that this tensor consists of, and I can consist of, metric tensor, but not a metric tensor just because it's a dimensionless value, but some derivative, and the second derivative of the metric tensor. But we don't know which exactly construction should be. It can be like this, for example, or it can be combination like this. So it's the derivative of metric tensor multiply on the first derivative of metric tensor. Okay, let's write it like this. Again, I will remind that when we use this comma, it means that we speak about just a partial derivative. Okay, like this. So this kind of possibilities, this is scale homogeneous terms, and I will explain what it means. So this kind of combination correspond to the scale homogeneous terms. It means that such a kind of combination doesn't combinations don't depend on the on the scale which we choose. Because, for example, you can say, okay, but we also can consider such a kind of combination like metric tensor multiply, and this is metric tensor non-dimensional, multiply on dimensional term. So, for example, this is 1 divided L square. It's also correct, why not? So, from the point of dimension, we will obtain exactly what we want. Or, like this. So, this is the first derivation, so we already have a 1 divided on L, multiply 1 divided on L, okay? So this gives us finally the dimension 1 divided L square, and this gives us the dimension I divide on L square. But we don't like this, the second one. Why? And when the general relativity was built, it was also choose such a kind of suggestion. Why we don't like it? Because exactly this, if we will use this such a kind of terms, these terms scale in homogeneous. Why? And it will depend on the sum scale which we consider. For example, we need to take into account that, for example, if we are in this case much less than L, the sum scale, this summand will be small, so the corresponding summand will be small. And otherwise, if we are in a large scale, these values will be yes, right, will be larger. In principle, it can be built a theory like this, taking into account the scale. But we would like to build the equation and the theory such a way that this theory will be independent on the scale. All time when we try to generalize something, to build some general theory, we would like to be free from some additional constant, or from some inhomogeneous cases, which, you know, can influence on the final expression of the equation of the nature. So for the idea that we decide that we don't want to use to impose such a kind of dimensional scale in our theory. So we want to build theory which doesn't depend on the scale where we are working. Doesn't matter this is in vicinity of the Earth or this is on the scale of the universe. Suggesting that the nature like such kind of theory, but God knows. I just want to be honest with you how we built the theory. So the third one, the third property, we also can understand that this tensor should be symmetrical relative to permutation of its indexes. So GIK should be equal GKI. Why? But because on the right side we have a energy momentum tensor, and the properties of energy momentum tensor is such a way that this tensor is symmetric. Sorry, I didn't have time to do much more attention for the energy momentum tensor, but we will use it in the future for model of the universe. So, but we don't have a lot of time for our course to consider everything. So, but this is a property of the energy momentum tensor. And since it's symmetric, so it understands that this tensor also should be symmetric. Fourth property that we already even put it in the beginning when we decided to generalize the equation for the strong gravitational field, that zero component or time component of this tensor, this must be Laplacian of G00. And this is for the case of the weak gravitational field. We even have the fifth property, which is very important. This property come to us again from the property of energy momentum tensor, because since energy momentum tensor TIK, if we will take the covariant derivative like this equals 0. This equation for energy momentum tensor give us correspondent the energy conservation law when we speak about zero component equals 0. This give us energy conservation law. And for the space component, it's tell us about the conservation, the law of conservation of momentum. So this is property of tensor of energy momentum tensor. But it's immediately tell us, since we decided to find the equation in the form TIK. So it means that if we will put here I, and if this is 0 for this part, it means that GIK covariant I equal must be 0 too. And this is the fourth property of this tensor, which we put in the left part of our equation, which we would like to find. So if we will speak, and I already said to you before, that Einstein spent a lot of time to find the equation of gravity and it's look, as I remember, he spent 3 years to work with this very hard. He even wrote that the special relativity looks now is just simple problem comparison with this general relativity theory. There is a suggestion why, and so this is because Einstein understood well the first false properties of this tensor, which should be in the left part of the equation. But he doesn't know the combination. So the point, which combination of, sorry, it should be, such a function I can write like this of metric tensor. And to find this function of metric tensor, he knows this 1, 2, 3, 4 properties, but the fifth properties he didn't know this which is exactly expression should be, and he spent a lot of time with this. Maybe this is exactly why he says that he doesn't know mathematics well, like this, which sometimes used by stupid people to tell that Einstein was not so intelligent. Of course, he understands, again, I would like to say, understand mathematics well, but this tensor analysis mathematics was really something new, and as you understand, it's not so simple. So the point that in any case, we can, what we have now, I might say, I can say like in our luggage, So we have, we understand that this, we can understand that this tensor, it should be some combination of what we have, which object we have, which describe the space, and this is a tensor of the second rank. This is Ricci tensor, and this is scalar curvature. So we can say, okay, we can try to find this such a kind of expression, or this tensor in the form like this. Alpha is some constant, so this is Ricci tensor -1 divided, it will be understandable, y multiply on 2. Why we can, and later in principle we can do some procedure to find that alpha must be equal to unity, so it doesn't matter, we can even forget about this. I will not spend for this time. But why we can consider this, can even to kill here, why we can consider exactly this combination? Because before, if we will jump now in some previous lectures, this one, we obtain very important expression, which we call the second Bianchi identity, or differential Bianchi identity. Okay, this one, second Bianchi identity. Even in this case, so this one is it's even better, and we really can see now. I will exactly to put here So that this is exactly what we need. There is some combination which consists of the metric properties, the object which describe metric properties of the space, and exactly this combination give us the fact that covariant derivative from this combination equals 0. What we exactly need to satisfy this request that energy momentum tensor, its covariant derivative must be equal 0. So, and this is what now we call Einstein tensor. So this is really good because, as we know, C Bianchi identity, GIK covariant derivative I equal 0, which correspond to the case that TIK covariant I equals 0. So this exactly this Bianchi, second Bianchi identity, it looks like Einstein didn't know why he spent a lot of time to find this combination. And this is exactly his remarks about the fact that he didn't he didn't visit lectures a lot which are related with mathematics, and he was upset with this later because it was exactly what he needed to know. So sometimes it's happened. Okay, we can put it in again in frame. So it means that we can write finally Einstein equation. So from the left part we can put R IK minus 1 divided on 2 GIK R, and on the right side this is 8P G divided on C 4 TIK. So IK, so this is Einstein equation for gravitational field. Or you can use much shorter, just to write the GIK equal 8PG C4 TIK, the same. Understand what is a G. So, and again, usually when the people hear about Einstein equations, they immediately think that this is E equal mc square. But much more important, not much more, it's also important equation, but also important equation. So, and we need sometimes to clarify that Einstein equation for gravitational field. Also, there is we can revise this equation in another case, which also important. Okay, and you can also remark that the left part, this is describes the curvature of space-time from the left part. On the right part, we have the matter. So this is connection of the matter with the curvature of space-time. So if we have a matter curve space-time, and the curve space-time tell matter how to move. So, and this equation, as I already said, its equation is non-linear. Also, it's also useful to have equation in another form. It's also very famous representation of equation for gravitational field, and we will use it too. Maybe even in the next lecture, I will spend little time to speak about black holes. I just want to show the equation from which the black holes was born, in sense, from the point of theory. So, look, I will do the following. Here I will write the Einstein equation. I will explain what I want to do. I want to keep on the left part only Ricci tensor. Yeah, and you can describe in your conspect what is each object. So RIK, this is Ricci tensor. GIK, this is metric tensor. This is scalar curvature, and so on. So what I want to leave on the left part only Ricci tensor, and to do some procedures such a way that everything will go to the right side, but in representation of the matter property. So we will see now what I will do. For this, I will rewrite the Einstein equation. GIK. So I remember by heart that here I need to put 8p because this is memory from Poisson equation. 4p is from Poisson equation. Multiply on 2 because we consider it's a series of the square root. I need to remember to put gravitational constant. I need to put C in 4. If I don't remember this power, I can immediately to check the dimension of the left part with the right part. So C I understand because it's relativistic theory, and I put matter. Okay, so this is Einstein equation in this form. Now I want to make a swapping, so it means that I will multiply left and right part on GIL. So in this case, you can rewrite, but I will put this like this. So I will put just here GIL, GIL, GIL. Okay. So I can see that I have here. So I make a swapping. So it means that I will have R L K minus 1 divided on 2 J. Now J. Now look, since I have here GIN, GIL, so I will have finally unity tensor. Okay, and L. And this is not the N, this should be K. So it's very important to write. So I put K, which looks like N. So I write here delta LK R equal 8PG divided on C4 TLK. Now I will do again the swapping. What it means? I will put instead of K, I will put L. You can rewrite, okay, the new equation, but I will use this. So I will put here L, L, L. So, but you please rewrite in your conspect the new equation with the swapping. From this point, I can see that RLL, it will be R. It's a scalar curvature, it's because scalar curvature, this is exactly the swapping of the mixed Ricci tensor. minus 1 divided on 2. Delta LL will be equal 4. Because again, I will remind that delta ik, this is 1 as the I equal k, and 0 when I doesn't equal k. And since we have a 4 space-time, 4-dimensional space, so space and time, k equal from 0 to, to 3. So 0, 1, 2, 3. It means that when we are doing like this, opening of L, it will be 1 plus 1 plus 1 plus 1, because it's understandable. This is sum on the L, where L from 0 to 3. So we have here, this just to explain why we have here 4. Again, here we will have R, and repeat here. C4 multiply on, and TLL, this is will be just a T. So this is swapping of the mixed energy momentum tensor T. So, and we can see from this expression that what we have, it will be just here R minus 2R, which should be minus R. So we see from here that that R equal minus 8PGC4 multiply on T. This is, we obtain the expression of the scalar curvature through the swapping of tensor energy, the tensor momentum energy tensor. Now, if we will put it in our Einstein equation, so I will put it here again. I will remember that R R L K, I will use this representation, minus 1 divide delta L K R equal this is Einstein equation, and you can also to explain this. This is the Einstein equation, mixed form of Einstein equation, mixed form in the sense that we have here covariant and contravariant components. But instead of R, I will put exactly what we obtained here. So, and move it on the right side. It means that I can write the Einstein equation as the form R K L equal, so it will be a joint multiplier. Okay, so it will be TLK minus, in any case it will be here minus 1 divided on 2 delta LK on T. So this is also some of the form of Einstein equation, which is sometimes convenient. Why? Because, for example, if we have an empty space, it means that, why it's convenient? Because from the left side, you have only a Ricci tensor, and on the right side, you have this combination which are related with a matter. For the, let's consider that if we have empty space, it means that we don't have any distribution of the matter. So it means that T L, K equal 0, all components, we will obtain the equation of gravity will have a form. It's Ricci tensor equals 0. Or we can multiply on, if we will multiply, or make a swapping with covariant components. So I mean, to write like this, multiply on GIL, it will mean that for the empty space we will have an equation like this. This is, you can write that this is Einstein equation for empty space. And what is interesting that even if you have an empty space, the Einstein equation have a non-trivial solution. Einstein equation has no trivial solution. And this is exactly, it's a very important equation because exactly this Einstein equation give the solution if you will solve it for some general metric, spherically symmetric wave metric, you will obtain the metric which correspond to black holes. So black holes appear from this equation. That's right, black holes. Very simple, looks very simple. They like say that this is just three letters. But exactly this equation give you tell you that such a strange object, which we call black holes, really exist from the point of mathematics, from the point of not mathematics, from the point of theory of gravity. So maybe I will speak a little bit. I don't have a time to find the metric for this case, which is beautifully to find, and it can be. It's not complicated to find, but so we really can see that this equation allow to exist some special solution, but we will speak about some properties of such a kind of solution because it's important. Such a kind of solution which tell us that there is such a strange object in vicinity on which we have a strange effect like a deceleration of time, like some singularity and like this. So, even Einstein couldn't believe in the beginning, and he thought that there is such a problem in the theory due to the presence of the singularity for this solution. But finally, and now, and we can't. I would like to say that we can't explain many observational data without really suggestions that such a kind of exist. So black hole, this is hole in the space and time. I can say like this, and it's a really object which consists can create a lot of things. Like jets, like a powerful accretion disk, and we really can see it from some special object like a quark quasars and active galactic nuclears, and also as a result of collision of relativistic object which product the gravitational waves and like this. So, and this come to us exactly from this Einstein equation for the empty space. But empty space, it means that we have, so just to explain, because you can say, but it's empty, it's nothing. So this is solution, black holes appear in spherically symmetric solution of empty gravitational field, and it means that we have some object which create, for example, gravitational field, which now we call black holes, but around we don't have anything. So this is the point. So in spherical symmetric, to say it strictly, the spherically symmetric solution of such a kind of equation, which called Schwarzschild metric, I will speak a little on the next lecture, tell us that this non-trivial solution depend on only on the mass, and it's all, if we speak about only Schwarzschild solution. So we already have 20. So it's already time to finalize lectures. If you have a question, please ask me. I will make a screenshot of you present. And I will check about the additional lecture which university maybe posted already, and so I will see you. If we have for now only 2 lectures, we will meet with you on Friday. Okay? Okay, so are you here? Yes, because you know I didn't hear any noise, so but I hope that you are present and nothing happened with the screen and okay, so everything you was in time to repeat everything, so it was okay.
Okay.
Okay, so do you have some questions?
No.
No. Okay. So see you on Friday. If something will be happened, I will write you in Telegram. Please check it, because I'm sorry, but really sometimes I need to travel, and I try to organize everything such a way that to be in time to give lectures, but sometimes it's really physically impossible. And thank you very much for your understanding that you are ready to help me to move the lectures. So it's really important for me. Okay, so thank you also, and see you on Friday.